from the very stereotype of general definition, system can be defined as a group of objects. Those are joined together in some regular interaction or interdependence toward the accomplishment of the same purpose. This is very general definition, and we will represent this system in our simulation using the defined entity and related attributes and the activities. This activity trigger change the status of each entity and attributes. Actually, system is fundamentally a target that we are going to analyze. So we can have such kinds of examples. Firstly, the physical system that we can physically identify. And also the conceptual system can be one example of a system. It means that even though the target system is invisible, but the invisible system can be also a kind of a system. The example of the conceptual system can be a software or wait, I'm sorry. And also some business process can be a conceptual system. Also, there can be very various kinds of complex system, and also contradictory deformal system can be an example. Also, the many kinds of information system, such as ERP. ERP means enterprise resource planning, enterprise ERP, or APS, advanced planning and scheduling system, is a very good example of the information. Also, there can be a meta system. Meta system is the higher level definition. For example, any framework or architecture can be a meta system. And based on these kinds of meta system, the lower level or the actual application can be implemented. So the architecture of or software design or hardware design that can be the meta system. Also, solar system. It's not battery. It means that it means the sky. It's such kinds of sun or Jupiter or Mars. So solar system is a very, very gigantic system. And also the systems in human anatomy. It means our face or stomach or our liver. Those kinds of entity compose our body. So our body can be an example of the system. Or market, stock market, or any goods market. Every kinds of market can be described as a system. Also, in terms of the engineering, the thermodynamic systems can be an example of the systems. Okay, there can be a various the kinds of system, but we have to consider the difference between the discrete and continuous system. Firstly, discrete system have the characteristics of state variables change. at discrete points in time. So for example, number of students in this class can be made as a model with respect to the discrete system. When we have started, when we start our class in a new semester, so when you register a class, so when a registration or some addition is conducted, the number of students in this class will be increased. And in case of any drop, or when you abandon the class, at the case, number of students will be decreased. So the number of the change of the number of the students in some class can have a characteristic of discrete. And next, the continuous system. Its definition is state variables that compose the system change continuously over time. The continuous is the important terminology compared with the discrete. For example, the volume of the gas in the atmosphere or any fluid inside a closed tank can be described as a continuous system. When CO2 is being generated via people by breathing, the industries and natural events and is being consumed by plants. So this circulation that those are generated by human and consumed by any plants or consumed by another peoples, the circulation, the phenomenon can be defined as a continuous system. So in most cases, the models of continuous system typically use the difficult differential equations because in order to indicate the rate of change of the state variables, those compose the complex system, have to be investigated. So in order to describe the continuous change of the continuous system, the math equations or math definition is really required. One thing that have been noticed is that if we make the time increment and the unit of measurement small and enoughly, then we may be able to convert a continuous system into a discrete one. So when we convert the actual continuous system that is described by differential equation into a discrete system, any kind of simulation, at the times the transformation from continuous to discrete one. So also, the most systems are not necessarily exclusively discrete or redundancy or exclusively continuous. So we will be primarily concerned with discrete systems in this lecture. Okay, next is model. What is model? Model is the design result or implementation of the target system. So studies of systems can be conducted or accomplished with a model of a system. So very simply, system is one actual things, and the model is some kinds of virtual things. So model is a representation of a system for the purpose of studying the system. So when we go to here, when we are going to study or we are going to analysis of for example, the thermodynamic systems, at that case, we have to make a model that can present the behavior and the changes of the entity and attributes of thermodynamic systems. Okay, so model is the one that have to be made in order to analyze the target systems. And when we make a model, we have to consider the aspects of the system that affect the problem under consideration. It means that we can omit or we can exclude the things those are not related with our problem. So when we make a model for the system analysis, we have to define the entity. In case of solar systems, the entity can be our Earth or Mars or Sun. Those kinds of things can be entity. And also attributes is a data that is related with each entities. With the same example of solar systems, with respect to the Earth entity, the related attributes can be the size or diameter or the volume of the air or volume of the fluid, it means the water. Those kinds of things can be attributes related to relevant entities. Also, activity is the one that trigger the change of the state of its own entity or the other entities. For example, of the solar systems, the activity that is related with our Earth is or any kinds of what do you call the Earth or Mars or Jupiter? Those kinds of entity have their own gravity. This gravity gravity affect the motion of the other laws. So simply activity triggers the event and the change of the attributes of each entity. So those are the components of the system that we have to define in order to make a model. So in the terminology of a system model is a representation of the system to be used or to be studied in place of the actual system. So usually we simply call it just a model without the system word. But definitely by definition, model is originally comes from the system model, and this system model allows us to study a system it's important thing, without actually building the system. If we build the system actually, it could be very expensive and also very time consuming. So in this terms, the purpose of the system model is related with the economic aspect also. This is the diagram that is defined by Ober and Prince from the paper of what do we need meta models for. In this paper, we can find this diagram, and there is noted system and model. And it is a very good representation. It means that model abstracts the system. It means that any model that the purpose of the when the purpose of model is to investigate the relevant system, this model is made by selecting the important aspect of target system. So we can say the model abstracts the system. Also, there is two more things, theory and tools. Actually, theory is some formula or any framework or any methodology. Those have to be used for the make of the model. So we can say that the model is the actual instantiation of the relevant theory. In our class, our theory will be DES, Discrete Event Simulation. So when we make a model for the purpose of the factory analysis, at the times, this model is the instance that is implemented with the DES theory. Also, we need the tool for the model implementation. So this tool have to be prepared for the implementation of a relevant theory. So for example, the commercial software of DS, such kinds of the AnyLogic, Simio, or very famous Arena, or what do you know about commercial software? So any kinds of software for the DS have their own theory, and those commercial software, so it means the commercial tools already have the implemented theory. Also, these tools help us to make a model in more efficient way. So we can say this tool can handle our target model implementation. So this configuration is very, very good to understand the relation between model and system, also including the fundamental theory and also the implementation tools. In this lecture, we will use Python and the SymPy package as the DS tools. Okay, nextly we will go through the kinds of models. It means there is several several consideration of the definition of each model. So there can be physical model. Firstly, it means the physical model represent the system that is actually constructed or actually built. Can all of you hear me? So if we make a physical model that abstract our target system, at the times based on this physical model, many times of tests can be run on this model, and the result used to make decisions about our target system. So this is a very good example of physical model. Have you seen these kinds of things? This is the clay model. And this model, physical model, is made before, during the process of automotive design. And mostly, the actual 1-to-1 scale model is being made in order to see the shape, the overall shape, and the evaluation or some aesthetic the aesthetic evaluation can be conducted by using this clay model. It just have the external shape. There is no engines or there is no seat or steering. Only the external shape is being made because the purpose of this model is to check the visibility of the external shape. Also, in the naval engineering, this towing tank and the model ship can be an example of a physical model. This is the towing tank, and this is a scaled vessel that is being made by very small scale. And with this experiment, we can predict the dynamic behavior of the target, the ship design. Next is the mathematical model. Mathematical model represent the system by use of logical and mathematical relationships. Where is it? In simple example, you have already studied this equation at the high school period. This equation is to predict the distance traveled by object at time t when that object have the initial velocity and the constant acceleration. But when this is the example, and this equation is only available when initial velocity and acceleration is fixed. It means the deterministic. But if this velocity and acceleration is varied over time, at the times this velocity and acceleration have to be type of functions over time also. So mostly this mathematical model is very complex and have to be defined by entities and events in order to analysis in terms of the simulation. Or we have to solve this equation with the techniques of the differential method, equation method. Anyway, the mathematical model is the one that we will use in our discrete event simulation. Maybe you don't worry about how to implement this mathematics of the DS because our SymPy already have the kernel that is implemented based on DS mathematics. So anyway, by in dictionary terms, our discrete event simulation is the ones that the mathematical model terms. So in order to make this mathematical model to be useful, the model have to be evaluated or validated in some way. So there can be two kinds of evaluation methods. Firstly, the analytical ones. It means that when our mathematical model is not too complex, it means the relatively simple mathematical model, we can solve it in a closed form using the analytical method. One type of the analytical evaluation method is very famous Markov process or Markov chain. Those example can be seen in this address, but we can say the stock market. Stock market can be evaluated by define that system as a Markov process. Do you know Markov process? Markov process is defined as the entities of the components of a Markov chain is only affected by the just previous status of each entity. This is the definition of a Markov process. And by this simple definition, any systems that can be made as a Markov chain or Markov process can be made as a mathematical model. Usually, the model is represent as a type of array. Also, the weather prediction, or whether it will be rain or not, or it is sunny or not, gray. Those kinds of weather prediction can be defined as a mathematical model in terms of the Markov chain. So when we have to predict the weather, we can make very simple mathematical model based on Markov process. So anyway, the Markov process is one stereotype example of analytical evaluation, but most problems are too computation intensive to be practical in terms of the mathematical model or analytical evaluation. So we can see these kinds of things. Navier-Stokes equation. Navier-Stokes equation is still the one that is not analytically solved. Navier-Stokes equation can be only analyzed by the method of the discrete computation method. For example, computation fluid dynamics or any kinds of the commercial software, such kinds of the Star CCM or the Olga or ANSYS, any kinds of the commercial, the finite element, the software is to analyze these kinds of complex the system by simplifying to the discrete, the definition of the model. Also, the fluid structural interaction analysis is the one that cannot be analyzed as an analytical method. It means that fluid structural interaction phenomenon cannot be modeled as a closed forms. So when we say the fluid structural interaction analysis, this fluid behavior and structural behavior have to be splitted and make a very, very small unit of time. The interaction is defined in a discrete way. Also, in our case, it means that the analysis of the manufacturing system, the queuing models of queuing models is the one of the mathematical ones. The simple queuing model can be solved by analytic method. It means that by simple mathematics, but the real system, when we define the real system by use of queuing model, we cannot even define the formulated things with the queuing model with respect to the real system. So in this case, the simulation method is useful one. So in this case of the complex systems, we often use to simulation by defining the target system as a discrete ones. So for example, computational fluid dynamics or finite element method is the one that is the simulation method for the purpose of fluid dynamics or structural analysis. And in our case, DS is the one that is the simulation method. Nextly, there can be deterministic and stochastic model. It's very simple. Deterministic means that the input of the model is already known. So in this case of deterministic, no random variables are used. For example, customer arrivals to a store are monitored over a period of times. It means that it's not the stochastic distribution. This is an important term, monitored. If we can monitor the change of the number of customers exactly, we don't need to use the stochastic distribution. But practically, it's impossible, almost impossible. But in a definition terms, if we know the exact value at the times, we can make a model in a deterministic way. But most cases, the stochastics are required. In case of a stochastic model, one or more random variables have to be adapted in order to make a model. So result of the simulation with a stochastic model can only be interpreted as estimation of the true behavior of the system. So at this time, the quality of the predicted stochastic distribution is very, very important because it's directly affect the quality of the result by simulation. So different situation may require the different stochastic distributions. With the same example of the deterministic, customers arrive at a store with exponentially distributed IAT, inter-arrival times. This can be make a stochastic model. But before this, before the determination of this the distribution, we have to compare our target distribution and the actual data, or any kinds of the actual record from the real systems. In most cases, we do not know all of the input data in advance, and at least some random data have to be adapted in order to make the useful simulation model. Thus, our simulations will typically use the stochastics model, but please note that the deterministic ones can be used in case of planning validation. It means that in case of the scheduling and planning, they're already defined. Those targets already have the defined values, such kinds of the working duration or start date or finish date. At that case, we can use that the predetermined value. So fundamentally, and in terms of the experiment, the stochastic model have to be prepared, but in some case of the planning or scheduling or any other systems that have already exact known values, at the times the deterministic ones can be also used. So next is static versus dynamics. Static means that models of a system at a single point in time rather than over a period of time. It means that all the input and the result is calculated as the values at a single point in time. Sometimes Monte Carlo simulation is the ones very representative example of static model. It means that when we use Monte Carlo simulation, there is no chronological result. Only static result can be obtained with Monte Carlo simulation. Contradictory in case of dynamic model, it means that model status is varying over a time. And our discrete event simulation is rated with this dynamic model. So in summary, there can be three kinds of types rated with model. First is physical versus mathematical. Physical is the actual building versus mathematical means any kinds of mathematical formulation. And our simulation in this lecture is type of mathematical model. Next, deterministic and stochastic. Deterministic model have the already known values. And the stochastic model is used for the case of random variables with a stochastic distribution. Next is static and dynamics. Static simulation is the one with the Monte Carlo simulation. And the result of a static model is the data or is the number at a single point of time. And in case of a dynamic simulation, the status of the model is being changed continuously over time. And the models in this lecture, my summary is firstly, actually this is the more related with the systems. Anyway, discrete and mathematical and dynamic, and also here is the stochastic part, but in some cases, the deterministic model can be adapted also. So discrete, dynamic, stochastic plus the temporal deterministic approach can be used in our lecture. So from this slide is not published. It is just very similar, but a little bit different structure of explanation of a model. So I will quickly review the structure. Firstly, this kind of Cray model is belonging to physical ones. And sometimes we can also have these kinds of graphing models. But fundamentally, even these graphing models is more included in mathematical model because the most graphing models is being made based on the mathematical formulation, such kinds of curve or surface. And next is analytic models. For it's also related with is the higher level of mathematical. Anyway, this F equal MA is very famous and very the representative ones that is rated analytic models. And also we can have these kinds of empirical models that is belonging to mathematical ones. It means that this is the frictional coefficient. And this equation is defined based on the physical experiment. So we can split this mathematical model into analytic ones, also these kinds of empirical ones. And next, in simulation models. Fundamentally, most simulation models is fundamentally based on mathematics, and from this branch we can split to deterministic and stochastic, also continuous and discrete. So this is the example of the continuous ones. This is the example of the offshore and the pipe analysis. And in order to analyze the behavior, the internal, the multi-phase fluid inside of pipe, we have to assume a continuous. However, and in practically, the software for the purpose of these kinds of analysis, it means that the Olga is very famous software for the analysis of the pipe, the fluid behavior of inside the pipe. The actual implementation of those software is more close to discrete ones in practical way. But the basic theory is the continuous ones. Also, then our discrete image simulation is the discrete ones. And we have these discrete models. We have to, no, not we have, these discrete event simulation algorithms is to find their way. It means that the tracking the status of the change of each entity is being identified in terms of in discrete point of time. So in next or in future lecture, we will study about some details of this mechanism. Okay, so discrete event system, DS simulation will be implemented based on discrete and dynamic and stochastic or deterministic way. And inside of the simulation, the state variables of each entity change only at a discrete set of points in time, as you have shown in this figure. And also, this discrete event simulation is analyzed by numerical way rather than by analytical method. So this is the end of the explanation, is the explanation of the definition of the system and the kinds of various of aspect of models. And next is steps of simulation. So this is the unique ones. It means that based on the target analysis or target system, these overall steps can be changed. But this is very basic ones. So in this study, we will go through what kinds of steps exist in the simulation way. So first is to define the problem. It means that in step of problem formulation, we have to state the problem. What is problem? So our starting of the simulation study is being triggered by the state of the problem. So it means that the simulation analysts have to understand what problem is being issued. Next is the setting of objective and overall planning. So based on the problem, the objective of the simulation can be defined. It means that by defining the objective of the simulation, we have to be able to answer the problems. And also in these steps, we have to consider the availability of the simulation. The simulation is the appropriate ones or not. And some commercial cases, these kinds of the required the simulation engineers and cost or the period, implementation period have to be investigated, but in academic terms, this planning can be omitted. And next is the model conceptualization. Actually, conceptualization is a little bit difficult terms. Simply, it is design, initial design. So in order to make a model with respect to the target systems, we have to distill, it means select the important aspect of target systems. Those have to be transformed into the models. In order to that purpose, we have to select and modify the basic assumptions. So mostly the simulation analyst start with the simple model. And from the start of a simple model, the simulation analysis add the more complex and more consideration into the models. And next is the data collection. Actually, this is step 3, the model design and the data collection is being conducted in parallel way. In steps of data collection, a large portion of total time is required because in the viewpoint of simulation, the related data is splitted in initial times. For example, in case of the factory simulation, when we have to make a factory model, the related data is splitted away. For example, the product data is stored in CAD system, and also the machine data is being stored in ERP system, and also the throughput or any kinds of planning is being stored at the planning and scheduling system. So in order to make a model in terms of the simulation, those splitted data have to be collected. So this is a very boring thing, it requires boring effort. Anyway, so data collection is have to be beginning as early as possible. And next step is model translation. And translation is the same meaning with the implementation. So model translation means that make a model with a design from the model conceptualization. So the output of the step 3, model conceptualization, is a design draft for the simulation, and model translation is to use a commercial tools or use the development software. So in this case, mostly those kinds of commercial software or from the scratch way, the Visual Studio or in terms of the program language, C++ or C# or Python or Java, those kinds of language can be used for the model implementation. And next step is to verify and validation. I will explain in more detail of these two steps in later slide. When does our model is validated and verified, then we can have experience with the use of our developed models. This is the definition or differentiation between verification and validation. Usually, most people do not know the difference of these two terms, but let's think the difference between these two terms in our class. Verification means that the check the rightness of the model. It means that when we can say that our model is verified only when the running of the model have no errors. But in these steps of verification, the result of simulation is not checked, is not analyzed by the actual customer, our customer or actual shop floor yet. This kinds of evaluation of the rightness of the model is being conducted at validation steps. It means that we can say our model is validated only when our customer or the user of the simulation say that the result of this simulation model is reasonable or can be acceptable. So now can you find what is the difference between the terms now? So anyway, simply verification again means the model that have no errors, and validation means that the model have a right result or reasonable result. Okay. So when all these steps are completed, we can repeatedly run the model. And last is some kinds of documentation or implementation. This implementation does not mean the model. This implementation means the physical ones that is analyzed through the simulation analysis. So this is the last page of the steps of the simulation. But as I have mentioned in the start of this page, these steps can be varied in case by case.